Welcome. Today's lesson is on functions and function notation. By the end of the lesson, you'll be expected to identify, evaluate, and solve functions, determine which functions are one-to-one, use the vertical and horizontal line tests, and familiarize yourself with the graphs of the toolkit functions. We're not going to cover all of these toolkit functions today, but you will be expected to familiarize yourself with the functions on pages 16 and 17 of the required textbook. Let's start by defining a relation. A relation is a relationship between two variables. The independent variable and the dependent variable. The independent variable is usually denoted by the letter x. If you were looking at a graph, the independent variables would be the values along the horizontal axis. The dependent variable is usually denoted by the letter y. On a graph, these would be the values along the vertical axis. Now let's define a function. A function is a relation in which each output corresponds to exactly one input, or in other words, it's a relation in which each output leads to exactly one input. Now we can sketch what a function would look like below. We can also sketch what a function would not look like. So I'm going to scroll and zoom so we can see the rest of the page along with the definition of function, the definition we haven't filled in, and some information on function notation. So let's start with a quick sketch. Let's say our inputs are A, B, and C. This is my set of inputs. And here's my set of outputs, say R and S. I'm going to have A go to R, B go to S, and C will also go to S. Is this a function? Well, let's check the definition. Does each input lead to exactly one output? A leads to R, B leads to S, and C leads to S. So each input goes to only one place, only one letter. So this is a function. Now let's draw another sketch. Now my inputs are going to stay as A, B, C. I'm going to have outputs of R, S, T. A is going to go to R, B is going to go to S, and B is also going to go to T. C is not going to go anywhere. Let's label our outputs. Is this a function? A goes to only R, so that does not cause us a problem. B goes to S, but B also goes to R, and that's a problem. This single input of B leads to two outputs. The definition of a function tells us that each input must lead to exactly one output. So this is not a function. This brings us to the definition of a one-to-one function. A one-to-one function is a function in which each output corresponds to exactly one input. So let's do a quick example here. If these are my inputs, A, B, C, and my outputs R, S, T, I'm going to have A go to R, B go to S, and B also go to T. Oh, excuse me. C also go to S. If you notice, the output of S corresponds to two inputs. That is, both B and C lead to S. So this is not one-to-one. Let's quickly sketch out another example. If I have my inputs here and my outputs here, I have A, B, C, R, S, T. I'm going to have A go to R, B go to T, and C go to S. This is a one-to-one function. Each output can only be reached by one input. So this is a one-to-one. Now let's discuss function notation. The notation y equals f of x defines a function named f. You read this as a y equals f of x. The letter x represents the independent variable. The letter y represents the dependent variable. With that, let's look at the top of the second page of the notes for this section. Please bear with me while the pages zoom out and then zoom back in on the notes. So let's discuss determining if a table of values represents a function. Determine whether the tables below are functions. So let's look at A. -2 leads to 4. -1 leads to 1. 0 to 0, 1 to 1, and 2 to 4. It might be helpful to draw a little diagram of inputs. -2, -1, 0, 1, 2, and outputs. We have 4, 1, and 0. -2 leads to 4, and so does 2. But the question to ask, does each input lead to only one output? 2 only leads to 4, and -2 only leads to 4. So that's not a problem. Let's look at -1 and 1. They both lead to 1, but again, -1 only leads to 1, and +1 only leads to 1, so that's okay. And 0 only leads to 0, so this is a function. Now let's look at part B. I'm going to draw a little set of inputs and outputs. So let me scooch this word out of the way. There we go. So I have my inputs and my outputs. I have 0, 1, 2, 3, 4, and I have 0, 2, and 4. 2, or sorry, let's start with 0. 0 leads to 4. 1 leads to 2. 2 leads to 0. So far, no problems. Each input is leading to exactly one output. 3 leads to 4. Do we still have a function? We do, because 3 leads to only 4, 0 leads to only 4, and our last value here of 4 leads to 4. Again, we still have a function. 0 only leads to 4, 3 only leads to 4, and 4 only leads to 4. This is a function. Now I'll leave it up to the viewer to determine whether A and B are one-to-one functions or not. Let's look at example 1, part C. Let's sketch out our inputs and our outputs. We have -1, 0, 1, 2, and our outputs are 3. Actually, let's see. Let's get them in ascending order. -1, 0, 3, 5, 7. So -1 leads to 3. -1 leads to 7. Oh, and I'm going to stop right here. If you notice, we have 2 arrows originating at one input. That tells me that -1 leads to +3 and -1 leads to +7. Since one input leads to 2 outputs, this is not a function. And I don't have to draw any further arrows since I found enough of a reason to determine that this table is not a function. Now let's discuss the vertical line test. So the vertical line test can be used to determine whether a graph represents a function. Let's fill that in. So the vertical line test can be used to determine whether a graph represents a function. How does this work? As long as a vertical line intersects a graph only once, the graph is a function. So let's draw some vertical lines here. And I'm going to use red again. And I'm going to draw a few. You only need one. But for this first example, I'm going to draw a few. And notice that each vertical line only intercepts the graph one time. So if we're looking at our individual line, it only intersects our graph once, so we know this is a function. Let's look at our second example. I drew my vertical line, and no matter where I draw a vertical line, you'll see it's only going to intercept the graph once. So this is also a function. Now let's look at example C. Now this is a tricky one because every place I draw a vertical line, except for, well, let me scooch this over, here or here. Besides those two exceptions, everywhere I draw a vertical line, I will intersect this circle more than once. So this is not a function. Now let's interpret function notation. For example 3. A function, capital N equals f of y, gives the number of iPhones n sold in the year y. N is in millions. What does n of 2017 equals 216 and 76 hundredths represent? Let's recall our function notation. This would be of the form n of y. So this tells me that y is equal to 2017. And since y is in years, I know this is the year 2017. Okay, let's go a little further. Now I have n of 2017 equals 216 and 76 hundredths. We are told that this function gives the number of iPhones sold in a year. So this value here is the number of iPhones sold in 2017 in millions. Putting this all together, we have n of 2017 equals 216 and 76 hundredths represents the 216.76 million iPhones sold in 2017. With that, let's look at page 3 of the section 1.1 notes. So again, bear with me while the notes zoom all the way out, and then I will zoom back into an appropriate place on page 3. Let's discuss evaluating functions. When asked to evaluate a function, replace the variable in the formula with the value provided. We're replacing the independent variable. So for part A, everywhere you see the independent variable of x, replace it with a 1. We have f of 1 equals 1 squared plus 5 times 1 minus 14. So we have 1 plus 5 minus 14. 1 plus 5 is 6 minus 14. And this leads us to negative 8. So f of 1 is negative 8. Now let's look at part B. For part B, instead of a number, we're replacing our independent variable with another variable. So f of a is a squared plus 5a minus 14. And we're done here. There's nothing else to do, no like terms to combine. Let's look at part C. Now we're replacing our independent variable of x with the sum of two variables a plus h. So we have f of a plus h equals a plus h squared plus 5a plus h minus 14. And I'm going to skip a step here, but I'm going to write a little note. If this doesn't look familiar, then you should open up a Google window and type in perfect square trinomial. Recognizing perfect square trinomials is a great way to quickly factor or expand out when you see a product written like this. So this becomes a squared plus 2ah plus h squared plus 5a plus 5h minus 14. So now I'm going to take a look to see if I have any like terms. I don't. I have an a squared and h squared. They're not like terms. I have an a times h, an a, and an h. Those are not like terms. And I have a number, a constant. So I have no like terms, so I'm done. Now let's look at example 5, solving functions. Let me scroll up so we can see the rest of the notes. Perfect. So solving functions. Solve the function h of x equals x squared minus 2x for h of x equals 3. Here, this is the dependent variable, so we're replacing the dependent variable. So I write 3 equals x squared minus 2x. I can subtract 3 from both sides. Minus 3, minus 3, to end up with 0 equals x squared minus 2x minus 3. Now we can factor this. This is x minus 3, x plus 1. If you don't see how I got from this step to this step, you need to take some time to review factoring techniques. And again, opening up a Google window and typing in factoring techniques should bring up plenty of websites that can help. So now I have the product of x minus 3 and the product of x plus 1 is equal to 0. When the product of any number of terms gives us 0, we know that one of them, at least one of them, has to be 0. That's because any number multiplied by 0 is equal to 0. So this tells me that x minus 3 equals 0 and x plus 1 equals 0. So x equals 3 and x equals negative 1. I skipped a little step here. I added 3 to both sides here and subtracted 1 to both sides here. Now I know when h of x equals 3, x equals 3, and negative 1. I have 2 answers. Finally, we can evaluate and solve functions that are in tabular form. Here I have my function g of n. These are my dependent variables, my outputs, and my independent variables, my inputs. Evaluate g of 2. So I'm going to look here. This tells me that n equals 2. So I know when n equals 2, g of n equals 7. When n equals 2, g of 2 equals 7. So I'm done. I have just evaluated my function g for the input of n equals 2. Now let's solve g of n equals 4. So let's look down here at my dependent variables. I have 4 here and here. So I'm going to have 2 solutions again. N equals negative 1 and n equals positive 1. So when I know now when n equals negative 1, g of negative 1 equals 4, and when n equals positive 1, g of 1 equals positive 4. And that was simply by looking at the dependent variables and finding the corresponding independent variable or input value of negative 1 and positive 1. Now let's go ahead and take a look at the last page of the notes for section 1.1. Example 7, evaluating and solving functions using a graph. So here I have a graph of f of x. Let's finish labeling our axes. This is my x, or my independent variables, and here are my y's, also known as my f of x, dependent variables. Let's evaluate this function f when x equals -1. That's what this tells me here. This value in here is f of -1. So x is -1. I'm going to go along my x-axis, here's 0, to -1. And let's keep moving up or down, not down because this function isn't defined here. Let's move up. And notice that right here at the ordered pair or point -1, 2, I see that when I plug in a -1 to my function, the output is a +2. So this tells me f of -1 equals 2. Now we're going to solve this function f when f of x equals 0. So this is all the values along the horizontal axis, along the x-axis. Because what does it mean for f of x, for this vertical axis to equal 0? This means I can move left, I can move right, but I cannot move up and down. Because if I moved up and down, I would be moving or changing this value of f of x. And I'm told that f of x is 0. So there are 3 solutions here. One of them is here, here, and here. So let's start from right. Let's go from smallest to largest. So this first one is not quite on any exact value, but if you notice, we have 1, 2, 3, 4, 5 squares between -1 and -2. This tells me that this value is -1.2, comma 0 is this ordered pair. This other ordered pair in the middle is 0, comma 0. So this value is right at the origin. And then here I have 1, comma 0. This gives me my 3 solutions of x equals -1.2, x equals 0, and x equals 1. Now, let's discuss the final lesson of today, and that is the horizontal line test. So example 8, the horizontal line test. The horizontal line test can be used to determine whether a graph is a 1 to 1. And this is very similar to the vertical line test. If a horizontal line intersects a graph more than once, that graph is not 1 to 1. So I'm going to pull up a bright color, red, and I'm going to draw a horizontal line for example A. Notice that it intersects my graph in 2 places, so this is not 1 to 1. So for part B, I drew another horizontal line, and it only intersects the graph in 1 place. So this is a 1 to 1. And finally, my circle, I'm going to draw my horizontal line, and it intersects my graph in 2 places. So this is not 1 to 1. Example 8 uses the same graphs that were used when we discussed the vertical line test, and that was in example 2 on page 2 of your notes. So if you want to go ahead and compare those examples, see which ones are functions, which are 1 to 1 functions, and which are not even functions at all. That would be a good exercise to do as soon as you are done with these notes.